question is related essentially to lattice energies and thinking about ionic bonding. So what I did is I gave you guys a bunch of data, different data points, bond energies for between two atoms, the heats of formation, the heats of sublimation, the ionization energy, and then the lattice energy as well. And what I wanted you to calculate, right, was the electron affinity for chlorine. You could always look it up, but this is kind of to get you to go through those steps and figure out what those values are in these cases. So the approach, right, to do is that, if we're thinking about just simply what the reaction is that we're talking about in this case, that reaction is, right, that we're taking sodium metal plus 1/2 chlorine gas, and we're forming solid sodium chloride, right? So straightforward reaction in these cases, but there's actually, to get what the lattice energy is of the whole system, we have to go through a variety of different steps. And so when you guys get to the thermal part, it'll probably be explained a little bit better in terms of like what Hess's law is and being able to, have some kind of diagram where if you know a bunch of the different parts of a reaction to get to a solution, right, you can then figure those things out. And that's what we're going to be doing in this case. So I believe the way that it was approached in lecture, right, is that you just break everything down into different steps. And so, the things to make clear in these instances, right, is like ionization energy, electron affinity, all of those processes are always done in the gas phase. So what we have to do is we have to, convert at least sodium metal into gaseous sodium, for that ionization energy to be valid, right? So those are the things to think about, is that even though we don't really talk about, the phases that certain, types of values are located in, right? Those are always going to be important, right? The, ionization of solid sodium is going to be different than ionization of gaseous sodium. And gaseous sodium is a lot easier to ionize and measure, right? And the measure is really the most important part in all of that to get that data. So the way that we would approach this, right, is that we would draw a free energy diagram here where we're going to transition through everything. So the first step, right, that we want to do is we're going to want to do the sublimation in this case to convert that sodium solid into sodium gas, right? So we're going to have that as a step. The next step, right, that we would have to do in this case, if we're just strictly focusing on sodium, is that we would want to ionize sodium in these cases. So for that, right, we would do the ionization energy of sodium to make sodium plus in the gas phase. The next thing that we would want to do in this case, right, so now sodium is set up to being sodium plus, right, which is the oxidation state that it has as sodium chloride in the lattice, is now we want to break apart chlorine gas, right, so Cl2 into individual chlorine atoms. And so to do that, right, we just simply take the bond energy, right, half of that would be part of the system. And so then now what we have is sodium plus gas plus Cl gas, right? So this right here is just going to be an individual chlorine atom, right? It's not going to be Cl2, it's an individual chlorine atom in this case now that we have. And so now we would have to then add an electron to that chlorine gas atom, right? And that's where the electron affinity comes in. And so now we have the electron affinity of chlorine on its own. So now what we get is sodium plus gas plus chlorine minus gas, right, in these cases. And then the final step, right, is that everything has to combine together to form the ionic lattice, which gives us the solid sodium, right? And so then this right here is going to then be the lattice energy for sodium chloride, right? So, looking at the values that we have, right, we have the value of sublimation for the sodium. We have the ionization energy for the sodium. It's given in electron volts, so we're going to have to convert that to kilojoules per mole, right, so that everything is in the same unit. We have the bond energy of chlorine, right? We have the electron affinity of chlorine, not in this table, right? So that's the thing that we're looking for, right? It's asking you here to get the electron affinity. So this is what we're aiming for in this case. And then what we have is the lattice energy of sodium chloride in that case right there as well. And then, you know, the thing to think about is that we also have then the delta H of formation, right? So that's essentially the value of everything going together, right, to form the sodium chloride, right? So the delta H of formation is the summation of all of those different steps together in these cases, right? So if we know all of, you know, everything except for one thing, we can then calculate what that one thing is. So if we set this up, right, we know that the delta H of formation of sodium chloride, right, is going to have to be equal to the delta H of sublimation for sodium plus the ionization energy of sodium plus 1/2 of the bond energy of Cl2 plus the electron affinity of Cl plus the lattice energy, right? So I'll just shorten the lattice energy to Le in this case of sodium chloride, right? So all of these things, together should give us that value. So because we're aiming for this guy right here, right, we can just rearrange the full equation so that what we have now is just simply the electron affinity of chlorine is equal to delta HF of sodium chloride minus the rest of this stuff right here, right? So I can put all of that just simply in parentheses to make my life easier. Right, sodium plus the ionization energy of sodium plus 1/2 bond energy plus the lattice energy of sodium chloride, right? And now one thing I want to, you know, be very specific on is that the bond energy, right, you have to only have half of it, right? Because the bond energy involves forming both, is in between like both of the chlorine atoms, but you only need half the equivalence of Cl2, right? Because you're only looking to make one individual Cl, right, for everything to balance out. And so, you know, based off of stoichiometry, you're gonna be multiplying the bond energy in half in this specific instance. So, So if we go through with all of this, what we have is then, you know, plugging in all of the numbers. We have for the delta H of formation, the value that we have is negative 413 kilojoules per mole minus, and so now the delta H of sublimation is 109 kilojoules per mole plus the ionization energy of sodium, right, is 5.14 electron volts. Now, one important thing, right, when doing this conversion is that the first step of converting electron volts into kilojoules per mole is first we're going to need to convert that into joules, right? So this has to get converted into joules in this case. So 5.14 electron volts times, and if I look up what that value is from the week 1 packet, right? So hopefully, right? So just brief detour. Exams next week, it's open note and everything. You can have your own equation sheet. I would recommend making your own equation sheet, not relying on one provided by us, because then that way you can organize everything in a way that it works for you. And then that way you know where everything is too. Just saying. Right. So what we have is 1.60218 times 10 to the negative 19 joules over 1 electron volt. And so what that value is 5.14 times 1.60218 times 10 to the negative 19 comes out to being 8.23. Oh yeah, there's only 3 sig figs. So it would be 8.24 times 10 to the negative 19 joules, right? So that's for only one atom, right? So now what we have to do is multiply this by Avogadro's number, right? So that way it becomes, joules per mole in that case, right? So we're going to take that number because this is 8.24 times 10 to the negative 19 joules per atom, right? We multiply that then by 6.02 times 10 to the 23rd atoms per mole, right? That comes out to being 8.24 times 10 to the negative 19 times 6.02 times 10 to the 23rd. That comes out to being 496,048 joules per mole, right? We convert that into kilojoules, so we just divide that by 1,000. And so what we get is the ionization energy is equal to 496 kilojoules per mole, right? So sig figs, there should only be 3 of them in this case. So plus 496 kilojoules per mole plus, right, 1/2 of the bond energy of Cl2, right? So that's 239 divided by 2, so that comes out to being 119.5. Plus the lattice energy, which is negative 789 kilojoules per mole, right? So we have all that. We just plug all of this into our calculator. So negative 413 minus 109 plus 496 plus negative 789 comes out to being negative 348.5 kilojoules per mole, right? So that's the value of the electron affinity of Cl going through that process, right? And so as I say also in the problem, right, the published value is negative 349 kilojoules per mole, right? So it matches, right? So this not baloney or anything, right? You're able to get to that answer in this case. And so that's all these steps are in these cases, is building out what all the steps are to go from point A to point B, right? You're not going the direct way. I mean, you can, right? That's the delta H of formation. But if you're like, well, I actually need to know one of the values in between or something, or if you don't know what the delta H of formation is, which I think is what the next part is going to be, you can go through that process in those cases, right? And you can figure out those values. So that's how you approach, these types of problems. And so part B, now it's, a hypothetical molecule. So this is a scenario, right, where you are making Na, 2 plus Cl2 is the goal. And so the question is, what is the, delta H of formation for this hypothetical molecule right here, right? Where you have sodium actually in a 2 plus state in a lattice together with Cl2. And so one thing, that's important is to transfer over the electron affinity value for Cl that we have from that first problem, right? You can either transfer over, the value that you calculated yourself, or you can take the experiment, the published value of negative 349. I'm just going to take the published value of 349, right? So EA of Cl is negative 349 kilojoules per mole, right? And then another thing I'm going to do is I'm going to transfer over the ionization energy for the sodium, because that's important, right? So that was 496 kilojoules per mole, right? And then we also have then the second ionization energy, right? So the ionization energy of Na plus to form Na2 plus, right, is 47.3 electron volts. And so I'm just going to go ahead and calculate that real quick for myself, right? So that way that's in kilojoules per mole. So if we take 47.3 electron volts, right? We multiply that by, 1.60218 times 10 to the negative 19 joules, right? EVs cancel. What we get is 47.3 times 1.60218 times 10 to the negative 19 comes out to 7.58 times 10 to the negative 18 joules, right? And that's going to be joules per atom then. Multiply that by Avogadro's number, so 6.02 times 10 to the 23rd atoms over moles, right? Atoms cancel, so what we get then is 7.58 times 10 to the negative 18 times 6.02 times 10 to the 23rd comes out to being 4563160 joules per mole, right? And so if we convert that then into kilojoules, right, divide that by 1,000, what we get is 4,563 kilojoules per mole, right? So, you know, based off of something that we had done last week, right, you can see that, you know, there's a tenfold jump between the first and the second ionization energy for sodium, which makes sense, right? Because, you know, sodium plus has what is it? Argon's electronic configuration, right? The noble gas configuration. So taking one electron out of that should be pretty unfavorable in comparison. So, right, which is why you see suddenly like such a massive jump, right? A tenfold jump in that case. So yeah, so we have this right here. And so then the thing that we would want to do, right, is just do the same setup that we had done before. So in this case right here, another thing to point out is that we're not going to be using the delta H of formation of sodium chloride, right? The delta H of formation well, we're calculating the delta H formation, but in terms of the lattice energy, yeah, I didn't copy that over. We're going to be, you know, substituting in the lattice energy of magnesium chloride. Right, and we're just simply doing that because, you know, in our minds we can make the argument that magnesium is the one that's, you know, directly to the right of sodium in the periodic table, and so, you know, going, you know, in these cases they may be a bit closer together in terms of what the values can be. But again, right, we're making a hypothetical model right here, so it's not necessarily going to be, you know, a perfect real world example because, you know, this isn't actually something that exists. But if we go through, right, and we do the steps, so the steps that we have, right, is that we're going to be taking, again, sodium salt, and we're going to be reacting this now with a full equivalent of chlorine gas, right? And that's then going to be forming NaCl2 gas. In this case right here, oh, not gas, sorry, solid. Right, and so, you know, right here what we're going to have is the delta H of formation, and we're just going to, you know, substitute in and say that the delta H of formation, or no, that's what we're trying to calculate, is the delta H of formation. Sorry, I just keep getting messed up in my mind, right? So we're trying to figure out the delta H of formation for sodium, you know, dichloride in this case. And so again, the steps that we do is the first step that we would want to do is if we just focus strictly on this, on the what has to happen to the sodium. So the sodium has to, you know, undergo sublimation, right? Because we have to convert it into the gas phase. And so now we have, you know, sodium gas plus Cl2 gas. The next step that we would have to do, right, is we're going to do the first ionization energy. So we're going to do the ionization energy of sodium to sodium plus. So that gives us Na plus gas plus Cl2 gas. Because the sodium is going to be in the 2+ oxidation state, we have to now do the second ionization energy. So if we do the ionization energy of Na plus, right, what we should get is Na2 plus gas plus Cl2 gas, right? So now the sodium is all set up, right? We're at sodium 2+, it's in the gas phase. Excuse me. So the next step that we would want to do is we now want to break apart the chlorine bond, right? The chlorine gas bond, right? The Cl2 bond into 2 individual chlorine atoms. So this is going to now be the bond energy. And in this case, right, because it's, you know, the stoichiometry is we're going to be taking one molecule for every, you know, sodium molecule, right? We're going to be taking one molecule of Cl2 and converting that into 2 Cls, right? Is going to be a 1-to-1 ratio for the bond energy, right? So that stays exactly the same. So what we get is then sodium 2+ plus 2 Cl gas in this case. And so that's going to go and get converted now. So now what we have to do is going to be doing the ionization, not the ionization, sorry, doing the electron affinity, right? We're going to be adding an electron to each one of those chlorine atoms. And so this now is going to be 2 times the electron affinity of Cl, right? Because there's going to be 2 of them that have to get electrons in this case, right, for this whole sequence. And so that's an important step to think about, is that because it's 2 chlorine atoms, right, each one of those chlorine atoms then has to absorb an electron for us to get what we need to get. And so then what we get then is sodium 2 plus gas, plus 2 Cl minus gas, right? So we have all of that. And then the last step is going to be the lattice energy. And this is where we're going to be using the magnesium chloride lattice energy as a substitute in this case, right? And so that's the whole process that we're going through. We're going from, both of them in their standard states, right? Sodium as a solid, chlorine as a gas. And then, subliming the sodium, ionizing it twice, breaking apart the chlorine gas into 2 individual chlorine atoms, adding an electron to each one of those chlorine atoms to form the Cl minus gas ions, and then doing the lattice energy, right, where they all go together and then they form the solid. So again, same thing as before, right? The way that we set this up is that we have the delta H of formation of sodium dichloride is going to be equal to the delta H of sublimation of sodium, right? It's going to be equal to, and then plus the ionization energy of sodium plus the ionization energy of sodium plus, right? So that's the second ionization energy plus the bond energy of Cl2 plus 2 times, and that's an important thing again, the electron affinity of Cl plus the lattice energy of magnesium chloride, since that's going to be our proxy in value in that case. And so now, right, we just take the values that we have and we just plug them in, right? And we just add it all up. So delta H of sublimation is 109 kilojoules per mole plus the ionization energy, which is 496 kilojoules per mole, plus the second ionization energy, which is 4,563 kilojoules per mole, plus the bond energy of chlorine, which is 239 kilojoules per mole, plus 2 times the electron affinity of chlorine, which is negative 349 kilojoules per mole, plus the lattice energy of magnesium chloride, which is negative 2,310 kilojoules per mole, right? So we have all of that, and we just plug in all these values. So we get is 109 plus 496 plus 4,563 plus 239 plus 2 times negative 349 plus negative 2,310. And so what you should get is essentially 2,400 kilojoules per mole, right? And I believe that's what I have on the key. Yes, right? So you should get about 2,400 kilojoules per mole, right? So that's the delta H of formation. If you have taken any kind of thermochemistry stuff in the past, right, and you're aware of like delta G and all of those different values, that should track with what you would expect, because when you have positive values for delta H of formation, or especially delta G and so forth, those are going to be unfavorable, right? Because you would rather lose heat, right? You'd rather lose energy and stabilize yourself further and be in a lower energy state than in a higher energy state. Whereas in this case right here, right, you're a positive 2,400. Whereas if you look at the delta H of formation for sodium chloride, right, that's a negative 413, which is a favorable value, right, in those cases. So right, so that tracks, right? So 2,400 kilojoules per mole is an expected value. And again, right, that's the same setup that we had done for the previous part of the problem. We just simply work our way through, right? We're saying like these are all the different steps that we have to do, and it's the exact same for every one of these ionic problems. There's no difference in terms of the setup. The only thing you really have to pay attention to is making sure that you're, thinking about stoichiometry, and that you're thinking about and using the appropriate values, right? So a common thing that people, I think, last year semester had messed up on when they were like thinking about this problem, and it may have happened this semester as well, was they weren't thinking about that you have to include that second ionization step, right? In these cases, right? They just simply multiplied the ionization energy of sodium twice, right? But that's just the first ionization step, right? So as we, we're talking about last week, second ionization is always going to be higher, and especially if it's a jump from, by row, essentially as what your starting point is. So yeah, but that's how you apply. That's how you do A3.